Let's look at number 1. How many moles of magnesium chloride are present in 60 mils of a 2 molar magnesium chloride solution? So when I saw 2 molar, I started thinking about creating a conversion factor. We could say there's 2 moles of magnesium chloride per 1 liter of the solution, or I could flip that and write 1 liter has 2 moles of magnesium chloride. I started with the standalone piece of information, the 60 mils. I converted it to liters, and then I grabbed this conversion factor here so that my units were canceling. So milliliters will cancel milliliters, liters with liters, leaving us with moles of magnesium chloride. So at the end of the day, we have 0.120 moles of magnesium chloride in the 60 mils. The second part of the question is where it gets a little bit interesting. So there's this assumption in the longer version of the problem that the magnesium chloride breaks apart completely. So when magnesium chloride breaks apart, we expect three ions. They're not different from one another, but 3 ions to form. We're going to have magnesium, chloride, and because of the subscript of 2, I'm actually going to get twice as many chlorides forming. So I'm going to use that, or you can think of it as a formula conversion factor to solve the second part of the problem. The setup in the beginning looks the same. We have 60 mils, 1 liter has 1,000 mils. I can use this same 2.00 moles of magnesium chloride per 1 liter. By all means, if the problem builds like this, we could have just started it from the previous answer too. I just want to show you the setup just in case they only asked you the second part. Now, here's where that formula piece comes in, or thinking about how it's splitting up. For every 1 mole of magnesium chloride, that's going to allow me to cancel out moles of magnesium chloride. We expect 2 moles of chloride. And we know that because of the subscript of 2 in the formula. So my answer here is 0.240 moles of chloride in that solution. Such a cool problem. So we're given this recipe for Ringer solution. It's used to treat wounds and burns. And we're told that in order to prepare 500 milliliters of this solution, you're going to need the following masses of sodium chloride, potassium chloride, and calcium chloride. So we're given a very specific recipe with masses and a volume of 500 milliliters. We're asked at the end of the day to calculate the concentration or molarity of each component ion. So remember, all of these ionic compounds listed here are soluble. So they're going to break into their respective ions once they're mixed into the water. So what I did was I went ahead and calculated the masses, the formula masses of each compound, and then used my conversion factors to change each of the masses into their respective moles. I know I wrote this just to follow my canceling. Grams of sodium chloride cancels with grams of sodium chloride. So I wrote this as moles of sodium chloride. However, the ratio of sodium to chloride in this compound is 1:1. So I could set up more conversion factors using this formula, or I could just think. Here's my thought bubble. Because it's 1:1, I expect 0.07359 moles of sodium ion, and that same value of chloride ion. So the compounds that are 1-to-1 are a little bit more straightforward. So potassium chloride is going to work the same way. I'm going to jump into calculating the concentration of the sodium ion in the ringer solution. We need to hold off on chloride for a moment because chloride comes out in every single one of the reagents. So that's going to be a little bit trickier. But since there's only one source of sodium ion, it's from the sodium chloride, we can go ahead and do that. So square brackets stand for concentration in molarity. So the molarity of the sodium ion is going to equal the moles of sodium ion divided by 0.500 liters, because they told us 500 mils. And so I got a concentration of sodium ion at 0.147 molar. I'm going to set up potassium the same way and calcium the same way. And then we'll come back to discuss what's going on with chloride. So the last thing we're going to do is calculate the concentration of chloride ion in the ringer solution. In order to do that, we need to figure out the total moles of chloride by adding up all of the individual contributions. So for sodium chloride, it's a 1-to-1, so I can grab the same mole value that applies to sodium chloride as a whole. That will also apply to chloride ion. So I'll do 0.073579. And then for potassium chloride, it's 1-to-1 again, so I'm just going to grab this value. And then we have calcium chloride. So I put a star on my work for calcium chloride. In this first step here, I just took the mass of calcium chloride that we were given, used the molar mass, and converted it over to moles of calcium chloride as a whole. Whenever you're thinking about what's going on with individual ions, you want to utilize those conversion factors that you can create from your formulas. So to figure out what's going on with calcium, I saw that there's a subscript of 1 that's understood with calcium. So I was able to say that there's 1 mole of calcium ion per every 1 mole of calcium chloride. The chloride, however, since there's a subscript of 2, I need to do a 2-to-1 ratio with respect to the calcium chloride as a whole. Basically, if you put 1 unit of calcium chloride into the solution, 2 chlorides are going to come off of that 1 unit. So you're doubling the molar quantity when it starts breaking up. So I'm going to use this number down here, 2.9735 times 10 to the negative third. So up here in the numerator, this represents my total moles of chloride. And then I'm going to divide by the 0.500 liters. Either use a big parentheses or do it in 2 steps. I got 7.856457 times 10 to the negative 2 moles of chloride. And at the end of the day, that corresponds to a concentration of 0.157 molar for the chloride. How would you prepare 500 milliliters of a 0.330 molar calcium chloride solution from solid calcium chloride? The first thing we need to figure out is what mass of the solid calcium chloride do we need? I'm going to use the conversion factor approach. So I'm thinking about this concentration as a conversion factor. 0.330 moles of calcium chloride need to be in every 1 liter of that solution. We're asked to prepare 500 milliliters. So I'll start my dimensional analysis with that number out front. I need to go to liters first, right? So 1,000 milliliters in 1 liter. After that, I can grab our conversion factor. Let's see where we're at in terms of units here. So milliliters will cancel milliliters, liters with liters, and now we're at moles of calcium chloride. We're getting there, but this is a lab scenario. This is a realistic situation that chemists and biologists encounter pretty much every day in the lab. So moles is not going to help us prepare the solution. We need grams so we can throw that onto our scale. So the last conversion factor I'm going to use is the molar mass of calcium chloride. So 110.98 grams, my thought bubble's in the way, of calcium chloride per 1 mole of calcium chloride. Perfect. Now we got rid of moles, and now we're in grams. We're going to need around 18.3 grams of calcium chloride to prepare this solution. Let's talk logistics. The question asked us to describe the steps and the kind of equipment we will need to prepare this solution. So the first thing you're going to want to do is grab a flask that is appropriately sized. So the volumetric flasks are only good for 1 volume. This is a 250 milliliter volumetric flask that I have in my hand. And there's a little line at the top that's called the scratch line. And if I fill so that the meniscus is right on the top of that scratch line, then I can be assured that I have, in this case, exactly 250 milliliters. For this problem, I want to grab a slightly larger volumetric flask, and then I want to make sure that I get 18.3 grams of calcium chloride into the flask. So I'm going to accomplish that by massing the calcium chloride directly into the flask. Like, I don't want to go ahead, mass the calcium chloride on the scale, and then carry it over and try to like shake it into the flask. The best way to prepare this solution, if you have a scale that can handle it, is put the volumetric flask on the scale. Use something like a powder funnel. I only have this funnel at home, so bear with me. A powder funnel would have a slightly larger bottom. So you put your powder funnel, and then you're massing into here. And so that way you could be assured that as your scale's moving up, that all 18.3 grams are actually in there, as long as you're not making a mess around the edges. Don't have a powder funnel, and a lot of times chemists don't even bother with the powder funnel because who wants to clean glassware? They take a piece of wax paper, or I've seen shiny, glossy, like magazine papers cut into small squares, and you can create an impromptu funnel to help you get that solid into your volumetric flask. The thing is, you want to avoid making the mess on the sides of the scale, because if the calcium chloride lands on the scale, then that's going to still count towards your mass, but it's not going to be in the in the volumetric flask, your solution concentration is going to be wrong. So you want to be nice and neat when you're doing this. So you're putting your 18.3 grams of calcium chloride into the flask. You know, sometimes I would tap the paper if like any of it got stuck or anything. So you're done with that. You got your mass in there. Now, you're going to add some amount of DI water. I arbitrarily chose 100 mils, and I put approximately. I don't even measure the DI water during this step. However, you don't want to go anywhere near the total volume when you're adding this first aliquot of DI water. Maybe fill it halfway with DI water, or just throw some DI water in. The goal, you're gonna cap it and you'll start inverting it. The goal is to get the calcium chloride completely dissolved. Here's why we have to do 2 additions of water. Some compounds really love water, and when they disassociate into their ions, the ions can fit inside the cage of the water molecules. So we'll talk about intermolecular forces later on in the course, but water creates like this cage-like structure, and you see the beauty of it when you look at like solid water, like ice, right? It's a very symmetrical and cubic. And so there's this cage, and something like table salt, sodium chloride, it breaks into sodium, it breaks into chloride, and those ions are small enough that they fit into the cage created by the water molecule. So oddly enough, when you mix a certain quantity of table salt with a certain quantity of water, the volume actually decreases. Like, we can't add the 2 volumes and expect it to be the same. They take up less space when combined than if you added up their 2 volumes individually. They really, start snuggling in together. Not all compounds act like that. So I don't know off the top of my head how calcium chloride acts, but there's a possibility that the ions don't fit into the cage, or maybe they don't like to be near the water molecules. Maybe they're not sitting well together. So they'll push each other farther apart, and sometimes you experience an increase in volume when you mix 2 things. So it just depends on the nature of the ionic compound. So instead of trying to look it up or predict it, what we do is we just add a small amount of water and get that thing to dissolve, get the solid to dissolve, and then it either expands or everybody fits together really well, but you're not gonna go over your scratch line because you're nowhere near your scratch line. So beginning chemists, I've done it myself. You're in a rush, you're in organic lab or something like that, where time is really of the essence. You throw your solid in there and you fill it up to the 500 mils. Shake it, and then you're shocked because all of a sudden now your solution is like near the neck, high up above the scratch line. And you're like, whoa, that's not gonna be your desired concentration if that happens. Pre-dissolve, kind of went on a rant, but you all aren't in lab right now, so I want you to know this stuff. Pre-dissolve, once you get it dissolved, it's settled, it's decided what it's gonna do, and then at that point, you can fill it the rest of the way to the scratch line. Mix again, we want this to be nice and homogeneous, but you won't experience the expansion or the contraction of the total volume if you pre-dissolve your solid. This is an interesting problem because we're given a target ion concentration, but we're asked to figure out what to do with a particular salt, in this case cobalt 2 chloride dihydrate. So it's a hydrate. Let's go over how to write the formula and figure out the molar mass. So we have cobalt, I'm going to do a 2+ because of the Roman numeral, and then chloride. And so we're left with COCl2 after we crisscross down the charges. Dihydrate, so I know that this part of the compound has 2 molar equivalents of water. So I'm going to put a dot, 2H2O. In terms of the molar mass, we have 1 cobalt, 2 chlorides, and 2 water molecules. And I'll just use a periodic table to look up all those values. When I added up all of the molar masses, or atomic masses, I got 165.87 grams for the molar mass of the cobalt chloride dihydrate. That's going to come in super handy as we're figuring out how to make this solution. So, again, this is a little bit backwards from what we've seen. I still want to take advantage of that conversion factor. So this piece of information right here, the fact that the chloride ion concentration is 2.0 molar, well, I can say there should be 2.0 moles of chloride per every 1 liter of solution. So I'm thinking about that conversion factor. Let me start with the volume then. So we have 100 milliliters of solution, and then there's 1,000 milliliters in each liter, just converting over to liters. And where to go? Let me grab that conversion factor. 2.0 moles of chloride for every 1 liter of solution. Well, these liters is gone. I don't have chloride ions though. I have cobalt 2 chloride dihydrate. So let me set up my next conversion factor to get rid of moles of chloride and change it into moles of the cobalt chloride dihydrate. So this is going to be one of those formula conversion factors. There's going to be 2 moles of chloride in every 1 mole of the hydrate. Now finally, I think I'm at a point where I can figure out the mass. I'm going to grab this molar mass conversion factor. So 1 mole of the hydrate contains 165.87 grams. I know it's annoying, it's probably even annoying while you're watching me, but we need to be very specific about the labels on all of our conversion factors. We have a lot going on with these problems. I got 16.6 grams of the cobalt chloride dihydrate. In problem 5, we're asked to describe the procedure for creating a dilution. First things first, use M1V1 equals M2V2 to calculate the volume of the stock solution that you need. And because these are corresponding pairs, I know that this volume, the 12.5 mils, specifically refers to the 3 molar calcium chloride. So everything's aqueous, so we don't need to do that pre-dissolving step that we saw with the previous problems. Instead, we're going to use an autopipette if you have access to one. And the autopipettes are extremely useful when you're dealing with smaller volumes, like 12.5 mils. When you get up to larger volumes, you're going to have to resort to using a graduated cylinder or maybe a volumetric pipette. There's other tools, but at this small volume, I'm going to hope that my lab has an auto pipette. But again, a graduated cylinder will work too. And we're going to use that to measure out 12.5 mils of the stock solution. We're going to add the stock solution to a 250 milliliter volumetric flask because that's how much of the diluted solution we desire. Now, with an auto pipette, there's a little button that you depress and it kind of pushes or forces the liquid out of the tip. And it depends on your technique and all of that. And I can explain it now, but it'll make more sense when we finally do get back into the lab and you have the opportunity to use an auto pipette. You don't have to worry so much about the liquid, the solution being trapped in the tip of the auto pipette. However, with a graduated cylinder, it's a different story because you all have a graduated cylinder in your lab kit. And you can imagine, like, when you're pouring out the solution, so much of it is getting stuck to the walls of the glass. So even though you might measure out 12.5 milliliters of solution using that graduated cylinder and you're spot on, some of it's going to get left behind in that graduated cylinder. So if the concentration is super, super important, you're going to want to rinse that graduated cylinder with some DI water and add the rinse into your 250 milliliter volumetric flask. And that ensures that all 12.5 mils got transferred over. Not necessary with the auto pipette though. Finally, the steps towards the ends are very similar. Fill DI water to the scratch line and you're going to make sure that you invert and mix to create a homogeneous solution. The last thing I want to mention in terms of problem number 5, what if you're in the lab and you don't have access to a 250 milliliter volumetric flask? Or maybe that level of precision, because the volumetric flask is going to be the most precise way to prepare that solution. What if that level of precision is just not that important to you at the moment? So the second thing that we need to think about when doing these dilution problems is how much water should we add? The scratch line is going to take care of it automatically if we use this approach. However, if you just measure out 12.5 milliliters of the 3 molar calcium chloride, throw it into a random beaker or random flask, and you're like, okay, now I'm going to measure out the water. How much water do you need? So you'll take your desired volume, the 250 mils, and you're going to subtract the amount of stock solution that you added. So you're going to have to add 237.5 mils of water. Maybe use a graduated cylinder to measure out that water if you don't have access to a volumetric flask. In number 7, we have 2 different solutions containing the same dissolved compound. However, they have different concentrations, and then we combine them. So this is analogous to a situation maybe where somebody made orange juice from concentrate, and they made it way too strong. And then somebody else made a second batch of orange juice, and they added way too much water, and the orange juice was way too weak. If you combine both of those pitchers of orange juice, you would expect to obtain an orange juice concentration that's somewhere in the middle, right? Like you would do that to remedy the situation. One batch is too weak, one batch is too strong. So if I mix it all together, maybe the mixture will be just right. And so we want to apply the same kind of thought process here. If we have 1.66 molar potassium permanganate and 0.892 molar potassium permanganate, and we combine those 2 solutions, then the concentration of the new solution should be somewhere in between. I went ahead and taking each respective piece of information, so the 35.2 mils and the 1.66 molar, I calculated the moles associated with that part of the mixture. And then I did the same thing for the 16.7 and 0.892 molar. Now our new solution, so this will be the molarity of, let me put mixture here, is going to be equal to the total moles divided by the total volume. So I'm going to add up the both mole quantities. And you can actually plug it into your calculator the way I'm writing this here, as long as you use the parentheses. So we have total moles in the numerator, and then in the denominator, yes, these are in milliliters, but let's just move the decimal place over. So we're gonna have 0.0352 liters plus 0.0167 liters. So total moles over total volume. And at the end of the day, that gave me a new concentration. So my molarity of my mixture wound up being equal to 1.41 molar. We always want to check that value in these types of problems where we're combining two things that already have their own concentrations, and make sure that the resulting concentration is somewhere in between. And it is. Seems reasonable enough, especially because we added more of the 1.66, so that's why it's a little bit higher rather than lower towards the 0.892. There wasn't as much of that 0.892. All of this is problem number 7. I separated it into two different parts because hopefully it'll make it a little bit easier to sort through what's going on. In part A, they told us that a student used 10 molar nitric acid to prepare 100 milliliters of a diluted solution. So the fact that it's a diluted solution makes me think, well, first off, what's the concentration of that diluted solution? That'd be good to know. So maybe I can use M1 V1 equals M2 V2 to figure out what's going on with that solution. There's so much information in this problem. They use 20 mils, let me call that V1, of the 10 molar. That looks like a pair, so I'll call the 10 molar M1. And then over here, this 100 mil will be a V2. And then I'm solving for M2. That'll be the concentration of the diluted solution. Plug and chug. So we have 10 molar times 20 mils equals M2, I don't know, so I'll just leave that as M2. But V2 is 100 mils, so I'll put that in. Divide over by 100 mils, and when I did that, I got a concentration of 2.00 molar. All right. That's the diluted solution. What happens is when you take a solution and you put it into a reaction mixture, or you combine it with other solutions, then you're changing the concentration a second time. Whenever you add additional solvent, additional water, any additional volume, the concentration is going to change. So this part gets a little bit tricky. I can still use M2 for my 2.00 molar solution. Let me jot that down. And the student used 4 milliliters of that 2.00 molar solution. So I'll call that V2 since they're a pair. Then they added it to 46 milliliters of reaction mixture. I need another volume because, again, I'm trying to find a concentration, so I'm headed in the direction of using M1 V1 equals M2 V2. V1, there's 46 mils in the reaction mixture, but V1 or V2, whatever you want to call it, the other volume needs to be a total volume. So it's 46 plus the 4 that they added for a total volume of 50 mils. And that's really important when you're looking at a dilution. It always has to be total volume. And then that would mean that I'm solving for M1, which will be the concentration of the nitric acid in the reaction mixture. So plugging everything in, we'll do 50 mils. V1, I don't know. M2 is from here. And V2, they told us, they grabbed 4 mils of that diluted solution. So when I went ahead and solved for what we're calling V1, but it's actually going to be the concentration of the nitric acid in the reaction mixture, I got 0.16 molar. Here we're looking at what's known as serial dilution. So in each of these steps of the dilution, I'm using M1V1 equals M2V2 to figure out what's going on with the concentration after that specific dilution. To kind of help me out, I made the subscripts more meaningful. So for instance, I used SS to stand for stock solution, or the subscript of B to stand for solution B. We're told that the chemist started with a 5.60 molar stock solution, and they took 46 mils of that, so I'll plug that in for volume. I'm looking for the concentration of solution A, and I know they diluted it up to 116 mils. So just using M1V1 equals M2V2 to figure out the concentration of A. Once we've established the concentration of A, it's around 2.2 molar, then we can bring that over to the second dilution, where they took 58 mils of the A solution, so 58 mils is my volume, and this 2.2 is from the first step. And they used that to prepare solution B, which had a total volume of 248 mils. Determined that the concentration of B was around 0.5 molar. Repeat this step again for the next dilution. So this concentration moves to the next part of the problem. That's going to be the molarity of B. We're going to want to grab the specific volume that they used. So they didn't use all 248 milliliters that they prepared. They only used 87 milliliters of the 0.5 molar solution. And so that's why here I multiplied 0.5 times 87. The new total volume is 287, and then that allows me to solve for the concentration of C. So at the end of the day, the concentration of C is 0.157 molar.